We've seen how to compare two different populations when we have two completely independent samples. In this video, I want to take a look at the other case. I introduced it in the previous video where we do have two different measurements where let's say we had some kind of test. So we're gonna do a test 1, and we have employee A, employee B, and employee C. And then we have some kind of intervening thing that happens in here, maybe a training program or time passes or some kind of incentive program or whatever. So we're going to have another test. So then we're going to have a second test. And so this kind of design is going to be called sometimes repeated measures. So repeated measures design. So after this intervening thing here, we're also going to have employees A, B, and C. So we're going to be able to track the changes between conditions of individual observations. Now, we could, just take the average. We might just be interested in the average for test 1, and then compare that to the average of test 2. But you can see how we're losing certain information. It could be that the averages are exactly the same, but that we have, A and B going up significantly, and then C just going down quite a bit. So it's going to be more informative to actually be able to see employee by employee what the changes were. And if we have a predominant increase in scores, then we would like to be able to capture that information. Okay, so this is what we do with a paired sample t-test. So last time we looked at independent samples t-tests, and we looked at some examples of those. So if you want to compare two things where you don't have repeated measures, we looked at the output of two factories. You might want to compare the day shift versus the night shift. Again, two completely different separate populations. And we might want to look at the difference between domestic developers versus outsourced developers in software performance. Okay, but the idea here is that these cases always involve independent samples, where we can't compare a single observation, let's say observation I, from one sample to the next. Okay. But in another case, we have related samples where they are dependent on each other, where we're looking at usually before and after. So the examples that I gave here are so the precision of a machine before and after repair. So you have machine A and machine B and machine C, and then you do some kind of tune-up, and you want to be able to track, well, let's go back to our bolt example. So are the machine's ability to conform to the specifications better after we do this repair? Okay, so we have a before and after case there. The number of customer complaints before and after employees receive training. So once again, we've got a before and after. Health plan costs before and after employee wellness incentives. Supposedly your healthcare costs go down if you can encourage employees to adopt healthy life behaviors. Well, this is something that you can actually track. Okay, so I want to demonstrate how to do a paired samples t-test by actually looking at a particular example and then going step by step through the hypothesis testing process, and then calculating the value of the test statistic, and then finally concluding with, as always, the Excel shortcut. But once again, the purpose of actually going through it step by step is to make clear the output of Excel, which I think if you just jump right to the Excel output is not always very straightforward. Okay, so here's an example of where we might employ a paired samples t-test. So your company has a customer service skills test with scores that range from 1 to 30. You test your employees before a 2-week class and then again after. Are the scores significantly better after the class? Okay, so let's go ahead and do what we did before and just go step by step and go through the hypothesis testing procedure. Okay. Okay, so the first thing we need to do is to set up our null and alternative hypotheses. So we have, again, we've got two different samples. We've got, population 1, mean for population 1, and mean for population 2. And our null hypothesis, well, before we get to the null, let's think about what would be the alternative, because sometimes it's more helpful to work backwards. Let's go back to the problem. Are the scores significantly better after the class? Okay, so we're interested in looking at if the scores improved. So this time we do have a directional hypothesis. So we want to reject the opposite of that. So let's figure out what the opposite of that is after we write down that alternative. So the scores are better after the class. So we will say that we'll call mu1 before, and we'll call mu2 after. So this would mean that our alternative is that before is going to be greater. Okay, so mu1 is less than, mu2. Okay, so this is what we're interested in. That is, so the scores before are lower than the scores afterwards. So we want to see if we can reject its opposite. So again, we can do some algebra here to slightly rewrite this and make this mu1 minus mu2 is less than 0. Okay, so the opposite of this is going to be mu1 greater than or equal to mu2. Okay, so you see we want to be able to reject that. So the alternative, another way of writing this so that we include a 0 is going to be mu1 minus mu2 greater than or equal to 0. Okay, now this particular statistic can be written in this case as mu sub d. Okay, so another way of stating this hypothesis, these hypotheses would be mu sub d greater than or equal to 0, with the alternative mu sub d is less than 0. Okay, so we want to see if we can reject the fact that that mu sub d is greater than or equal to 0, which would mean that the scores were higher in the first, the pre-test, the test that was administered before the training. Okay, so all right, we've got our hypotheses set up. So we need to specify the desired level of significance. Of course, we're going to do, we'll set that equal to 0.05 again. And our sample size. Okay, well, I've actually got some data here. So this is our, we've got 20 employees here, and we've got their scores before the lesson, so pre-lesson and post-lesson. And, we can kind of browse and see that if we just start going down the rows, that in most cases, they appear to go up. They seem to go down in a couple, but it looks pretty encouraging. But we need to get some statistics to make more precise this observation. So, okay, so our data is here. Our sample size now notice that when we were dealing with an independent samples t-test, we had n sub 1 and n sub 2. So we had two different samples. Now in this case, we do have two different tests, but we're going to just, because we treat each row as each as a particular employee, then we're going to just say, well, actually our sample size here is 20. We have a reading before and after, but we're going to say that our sample size is actually equal to 20. Okay, so n is equal to 20. Okay, so 3. So we need to determine the sampling distribution and our sample statistics. So once again, we are going to have a t-statistic. I mean, these are t-tests. We'll have a t-statistic. So it's going to follow a t-distribution. The sampling distribution will be a t-distribution. But remember that we have to specify the degrees of freedom. And I'll get into this when we look more specifically at how to calculate the t-statistic for paired samples. Okay. All right. So then step 4 is to determine the critical values. Now I'm going to go ahead and peek ahead to the next slide, which specifies how to actually calculate this, because down here at the bottom, it tells us that this t-statistic that we're going to calculate here is going to have n minus 1 degrees of freedom, where n is equal to the number of individuals. Okay, so that was 20 in our case, so we have 20 minus 1, we have 19 degrees of freedom. Okay, so now that's what we need to have if we're going to calculate the critical values ahead of time. And let's do that. Okay, so we have 19 degrees of freedom. So we need to figure out what are our, what's going to be our critical values. Okay, so as always, we try to remember what our distribution looks like under our null hypothesis. So our null hypothesis has it that the difference between the first and the second is going to be greater than or equal to 0. Okay, so we are going to be rejecting when we are down here, right? So if the null is true, then we're going to reject when we see a value that is significantly smaller than 0. Okay, so this is a one tail, right? So we just want one tail. So we need to find this critical value, and we're interested in whether our t-statistic is going to be less than whatever this left critical value is. Okay, so how do we find this left critical value? Well, as always, it's going to depend on our level of confidence, which is 0.05, and our degrees of freedom here. So we're going to go and use I'm going to use Excel to find this, but let me just write down the function really quick. Okay, so we're going to use T inverse, T inverse, and we are only interested in the this seemed to have been converted into straight lines, but this was a curve before. We're interested in this left critical value, and so we want to have, as always, 95% of the area over here, leaving 5% over here. Okay, so now because it's a one-tailed test, we don't divide this up and put some area over here. We just stick with 5. So now we're going to do T_INV 0.05, and then we just need our degrees of freedom, which is 19. Okay, so let's go into Excel real quick and find that. So we just need to do T inverse. Okay, probability 0.05 and degrees of freedom 19. Okay, so negative 1.73. Okay, so our critical value is negative 1.73. And we only need one because we're doing a one-tailed test. Okay, so so now we need to go on to the step number 5, which is to actually calculate the value of the test statistic. Now we'll take a look at the formula and then we'll do it in Excel. Okay, so we're interested in taking the difference. So these i's, this represents the rows. Okay, so each row in our data set, we had 20 rows, and each row is going to be represented as an I. Okay, so we're going to look at x1, that is, this is the pretest, the pretest value for observation I. Notice that this is not an aggregate, this is not a mean, this is actually for the ith row, take the value of the first test and subtract the value of the second test. And this gives us d sub I. Okay? So actually let's go piece by piece and go ahead and do that. So all we have to do is go row by row and subtract the first minus the second. Okay? So all right, we'll put d up here, d sub I. So that's just going to be the pre-lesson test. Actually, let me zoom in a little bit here. Okay, so it's just going to be equal to this one minus this one. Okay, so let's see if that makes sense. Okay, what this is saying is that if we subtract the second one from the first one, a negative number means that the second one was, that the second score was higher. Okay, so we can just copy this and paste it down for all 20 rows, all 20 i's. And I can see that based on the fact that most of them are negative, this means that the second scores tended to be higher. Okay, so that's d sub I. Okay, so that's that piece of it. Okay, so what we want to do now is to find out the d bar. Okay, now remember that bar just means average. So what we're looking at here is on average, what is the difference? Okay, and so you'll see that this is just the formula for the average, where we're adding up all the differences from 1 to n, right? N for us is 20, and then dividing it by 20. So this is just the average difference. Okay, so d bar is easy to find. We'll just find the average difference. Come over here. Okay, and I've got all the various expressions that I need over here. I'm going to put their values in orange. Okay, so what is d bar? D bar is just going to be the average difference. So I'll take the average of all these. Okay, so on average, people's scores went up too. Okay, now once again, this is not enough to draw a conclusion. Is that a significant difference? Okay, now the next thing we need is this, which is S sub d, but this is nothing more than the standard deviation of those differences. Okay, you may remember that this is the formula for standard deviation. That is, if you take all the differences from the observation to the mean, square those differences, add them all up, divide by n minus 1, and then take the square root, this is just the standard deviation of d. Okay, so rather than compute all this, I'm just going to find the standard deviation of d using the standard deviation function. So standard deviation, we'll use the S sample. So standard deviation of these. Okay, so the same d, just standard deviation. Okay, All right, so what is n? Well, we already know that that's 20, right? So our degrees of freedom was 19, okay? And we actually only need a left critical value here, okay? Because our alternative, we're interested in rejecting something that's out to the left there, okay? So our left critical value then was negative, what did we? Negative 1.73. Okay, negative 1.73. Okay. All right, we won't do p-value. Let's just ignore that. Okay, so then we've got d bar and we've got s sub d. Now, how do we combine these into a test statistic? Okay, so our final calculation of the value of the test statistic is this. We take the average difference and subtract the hypothesized difference. Now this was equal to 0. Okay, this is why we included the case of 0 in our null hypothesis, so that we are hypothesizing that the difference includes the case where there's 0 difference. Okay, so basically we're just going to take the average difference and then divide that by that standard deviation we calculated, and then divide it by the square root of the sample size. Okay, so let's do that. Okay, let's leave a blank here for our t statistic. So this is going to be equal to our d bar divided by our standard deviation over square root of sample size. Okay, do I have enough parens there? Okay, and so we wound up with a t statistic of negative 3.23. Okay, so remember that if we have a statistic that is more extreme than our critical value, our conclusion is to reject. Okay, so we can reject the null. Okay, so so now we step back and we go back into the management realm and we say, okay, well, what does this mean? We reject the hypothesis that the difference between the two is, let's go back, make sure we get this right. So our null hypothesis was that the scores on the pre-test were greater than or equal to the scores on the second test. Okay, so this is what we're rejecting. Okay, so we can reject the scores on the pre-lesson test were not less than or equal to the scores on the post-lesson test. The lesson appears to have increased scores. Okay, so there's our management. Okay, so and as usual, I want to show you the way that you can have a shorter route to these conclusions using what's built into Excel. So remember that most of what we want is here under the data ribbon, and I'm going to come up here to data analysis, and we see that we've got a t-test, a paired two sample for means. Okay, so paired, that's the clue that we're dealing with the paired samples here. So we'll click OK here. Variable 1 range, so I'm going to select the pre-lessons as variable 1. So this is my mu1 here. So variable 2 is the post-lesson. So these are the post-lesson scores, and these have to be the same size or else Excel will complain. I'm going to hypothesize that the difference is 0. Now remember that our null did include the case that they were 0 even though we were doing a one-tailed test. We set alpha equal to 0.05, and just so that I can see the results, I'm going to put set this as the output. Okay, and let's go ahead and take a look. Okay, So we look here, we didn't actually calculate the mean for the different variables because we were really more interested in the line by line difference. Okay, so we see here again that they calculated, I mean, they needed the degrees of freedom set it equal to 19 as we did. Their t statistic here was negative 3.23, which we calculated over here, using that formula on the slide. And we see that they did calculate a t critical value for one tail. Now, they only do it for one side. They don't give you the left and the right because they assume that you know that the left tail would just be the negative of that. Okay, so we did have the left critical value here, negative 1.73, so we rounded a little bit. So we were able to see that our t statistic was more extreme than our left critical value, which we could get from this. We would just have to say, okay, well, our hypothesis had it that we were interested in rejection on the left tail, so we would just do that. Okay, and again, if we also just wanted to do the one tail, the one tail p-value, we would draw the same conclusion because this is less than our alpha, which is 0.05. So this p-value, this one tail p-value, would tell us that we can reject at a 0.05 significance or 0.05 alpha. Okay. All right. So just to conclude and kind of wrap up what we've been talking about here with the all of these various t-tests. So just as a reminder, we had two different cases, depending on whether the samples were independent or whether they were paired. And within the independent, I said that we were always going to be dealing with the case where we can assume that the variances were the same. And so we used a pooled variance. But you see, if you look back in Excel, they also provide you a way to select a t-test to sample assuming unequal variances. Okay, and that's actually called a Welch's test. Okay, but the thing that these two cases had in common was that we were looking for a significant difference between two samples. Okay, now what we need to get in now is what if we are interested in the difference among three or more groups. So we compared factory A and factory B. Well, what do we do if we have three factories and we want to know if there's a significant difference in output? We can't really use the t-test anymore. And so that's what we use an ANOVA for, which we're going to get into next time.